Right, so in this video I'm going to talk about Euler's number, as it's sometimes called, and it's usually given the symbol E. So I'm going to start by looking at this here, investing €1 for 1 year at 100% interest rate. Let's start then. Okay, this is my timeline here, 1 year. Now if I invest €1 for 1 year at 100% interest rate, I'll come out the other end with €2. 100% of 1 is 1, added to 1 you get 2. So that's fairly straightforward. Okay, so now I decide, right, I really want the bank to calculate this 100% interest rate twice. So 6 months into the year, give me 50%, and then the other 6 months give me 50% as well. So how does that work? Well, I've got €1 put in at the beginning of the year, get 50% of that, added on. 6 months later I've got €1.50. So now I get 50% of this €1.50, added on, I get €2.25 at the end of the year. So you can see by compounding, by compounding twice throughout the year, rather than once at the end of the year, I've gone from €2 to €2.25. So it's increased. So let's look at compounding quarterly then. So I have €1 in there. At the beginning of the year, I get 25% interest at the end of the first 3 months. Added on, that's €1.25. Get 25% of this added on, I have €1.56. Get 25% of this added on, I end up with 1.95. Get 25% of this added on, I get €2.44. So you can see at the end of the year, in this case, I've gone from €2.25 up to €2.44. Now you might imagine that if I say to the bank, okay, compound it every week, every day, every minute, every second, that this will increase to some enormous value. But in actual fact what happens is it doesn't. There is a limit to this, and that limit is in fact E. And E is a number. I'll just write it out here. It's 2.718281828, and so on. It goes on forever. It doesn't repeat. It's an irrational number. So this will eventually reach this number E here, and that's really where E has come from originally. Now, if you were to, I've only done 4 calculations here, but you can do it. You can compound weekly, for example. If you compound weekly, then you will get an answer of 2.692597 euros. If you compound daily, you will get, this goes on forever as well, by the way, so you will get 2.714, 2.714567, and so on. So you can see we're getting closer and closer to this value here, but we are increasing quite dramatically the number of times that we compound. Now, there is what actually happens here is you start with your €1, you add on 1 over, say in the first case we added on 50%, so it's 1/2, and we compounded that twice. So this is what we started with. The second one, we had 1 plus, we added on 1/4 each time, we did that 4 times. So you can see the pattern here. What actually happens is you end up with this general formula for compounding here, which is this one here. Now, if you get the limit of this, as n goes to infinity, that will actually give us our value for E. So if you compound down to microseconds, if you like, you get closer and closer to this value E. Okay, so that's really where E originated, I guess. So let's have a look at another way of approximating this value E. Okay, so what I'm going to introduce now is something called the Maclaurin Series. It's a Taylor series. I'm not going to go into where it's come from exactly. I'll do that in another video. But we're looking at this thing here called the Maclauri, the Maclaurin Series. It's a Taylor series, really, T-A-Y-L-O-R, Taylor series. This is at x is equal to 0. So we're going to look at this one here. So this is f of x is equal to f of 0 plus f prime 0 at x plus f differentiated twice at 0 x squared over 2 factorial plus, I'll do one more, so you differentiate 3 times at 0, and that's going to be x cubed over 3 factorial, and so on. This is called the Maclaurin series, and what this does is it approximates functions. So I'm going to do an approximation for the function e to the power of x. So it converts your function into a polynomial, and you, depending on how many of these terms you require that you actually use, you can approximate your function more and more accurately. So what I'm going to do now is just look at e to the power of x. E to the power of x. So I'm going to take my function. My function is going to be e to the power of x, and I'm going to write out a polynomial for e to the power of x. So let's have a look at that. Okay, now in order to write this out, by the way, I should mention as well, this function e to the power of x, when you differentiate it, doesn't change. So if I get the first derivative of e to the power of x, I also get e to the power of x. So in other words, the slope of this function at any point x is equal to e to the power of x. It's equal to the function itself, if you like. So if I do a second derivative then of x, again I'll also get e to the power of x, and so on. So I can get the derivative of this many times I want, it'll never change. It'll always be e to the power of x. So I need f0. So I need f0 first of all. So if I put 0 in here, I get e to the power of 0, that's just going to be 1. If I get f prime 0 here, so the first derivative at 0, that's going to be e to the power of 0, which is also 1, and that's just going to continue on then. Each of these coefficients, in other words, of my polynomial will be 1. Now, let's just write out the series then. So my function then is f of x, and it is e to the power of x. And my polynomial then, it's going to look like this. F of 0 here is 1, so it's just going to be 1, plus f first derivative at 0 is also 1, and that's times x, plus the second derivative at 0 is also 1, but now I've got x squared over 2 factorial, plus this is going to be 1 again. Now I've got x cubed over 3 factorial, plus, and you can see the pattern, you just get x4 over 4 factorial, plus, and so on. So this is my Maclaurin series for my function e to the power of x. So this will give me an approximation for my function e to the power of x. So I can use as many terms as I like, depending on how accurate I want to be, to draw or indicate my function. Now, what I really want here, by the way, I can summarize this polynomial here. I'll just do that underneath here. I have my function here. My function f of x is equal to e to the power of x, and I can write that as the sum of, it is a sum here, it's a series, and it's a series with x's on the top here. So I've got x on the top, my numerator here is x. I've even got an x on top here if you like. It's x to the power of 0 here, x power 1 here, x power 2 here, x power 3, 4. So it's going to be x to the power of n here on top. And then underneath you can see that I've got factorials. Underneath here I've got 0 factorial, which is 1. Underneath here I've got 1 factorial, which is 1. 2 factorial, 3 factorial, 4 factorial. So this is just simply going to be n factorial on the bottom. And then I need to have n going to, n goes to 0, starts with 0, and it goes to infinity. So this kind of summarizes or encapsulates this this series here, this infinite series here. So this represents e to the power of x. Okay, so what we want is a value for e. So if I want e here, really what I'm looking at doing is looking at my function at x is equal to 1. So if I do f1 here, f of 1, that's going to be e to the power of 1, which is e, that's what I want. So in other words, wherever I see an x, put in 1. So what does that give me? Well, I've got 1 at the start here. X is going to be 1 here, so that's going to be 1. Here I've got plus 1 squared, which is 1 over 2 factorial. Then I've got 1 cubed here, which is 1 over 3 factorial. Then I've got 1 to the power of 4, which is again 1 over 4 factorial, plus, and so on. That goes on forever. So this will give me an approximation. This will give me my value for e. If I go on long enough, I'll get very close. Depending on how many decimal places I want my value for e to be, I just keep picking more and more terms here and working them out. So you can see here, this is my series for e, and remember that e is again, what was it? 2.718, 2.718, 2818, 281828. They're the easiest ones to remember, I guess, and it goes on and on forever. Okay, so if you look at what you've got here, you've got your 2 here anyway, 1 plus 1. So if I just take these two terms here, I have an approximation for e. Not a very good one, but it gives me 2 anyway. If I take the first 3, if I take these 3 here, they will also give me an approximation for e. So let me just work that out. That just gives me 2 plus a half. So it's 2.5, isn't it? 2.5. So here I'll end up with 2.5. Okay. Now if I take the next one then, let's say I take these 3 here, what do I end up with? I end up with 2.5 plus 1 over 3 factorial, which is 3 times 2 times 1, which is 6, so that's just 1 over 6. So that gives me 2.6 repeated, 6666. So you can see each time we have 2 here. So just put that in blue there. So that's 2 here. We've got 2.5, then 2.6666. So you can see each time we actually get closer and closer to e here. I'll just do one more. Let's see, what color will I do? Let's do this one. Okay, so let's take the next lot. So if I add these, so I have my 2.6666 and so on, and I'm adding 1 over, so I have 1 on top, I have 4 factorial on the bottom. That gives me 2.7083. So here I end up with 2.7083, and the 3 repeats. So you can see each time we pick an extra term, we get closer and closer to e, and you can see that these particular terms are getting smaller and smaller and smaller as we go out, because the denominator here is getting bigger and bigger. So we're adding smaller and smaller terms, and we will eventually reach very, very closely anyway to e. It will eventually get to e. If we go out into infinity, it will reach e. Okay, so that's it for this. Oh no, actually there's one other thing I just want to write out here. Let me just see if I can find that. Oh yeah, I just want to summarize this series here. So if we look at this series here, this can be written as again in sum notation here, so we got the sum here of, again we have all ones on the top, so it's going to be 1 over, what do you think it's going to be over? Well, it's going to be over something factorial, isn't it? So it is going to be over n factorial. So here we got n factorial here, and again what's n is going to go to infinity, so it's going to go from 0 out to infinity here. So this will summarize this particular series here. And that is it for this video.